Hello to everyone. Today I will be discussing electronic band spectra in absorption. Uh, the electronic absorption spectra of a diatomic molecule are often by passing continuous visible or ultraviolet light through a large tube containing the gas of the diatomic molecule, that is vapor container. You have a UV or the visible source, and this is a condensing lens, and this is a vapor tube in which you have a diatomic molecule or the gas. Then you have this at a small slit from here. Then this light is going. And from here you have a collimating lens. And after the collimating you have a grating. Then you have a spectrograph or the spectrometer and a photographic film. And initially these are recorded in the photographic film. And nowadays you have a spectrometer and the spectrograph. Then you are observing that absorption spectra of a gas molecules. These gas vapors are at a room temperature. At a room temperature, a typical absorption spectra found consists of an intense, extensive series of the bands which come more and more closer towards the wave numbers, higher wave number side, and ultimately merge into a continuum. So we'll see that these bands are coming, that initially that is very separated, and then finally they are merging towards the higher wave number side. And there is a very important differences between this absorption spectra, what we have done in previous class, that is the emission spectra. The emission sources of the band spectra are usually at a temperature higher than the room temperature. And so the large number of vibration levels of the exciting electronic state are appreciably populated. Hence the transition from the each of this new prime level varies to the new double prime level. Means because once it is a transmission, which this population is sufficiently high in these levels, and these energy transitions from this vibration level from all the levels of this excited level to all the level of this ground state one. Means both kind of the progressions you are given this. So you will be getting that once you have an emission spectra, you will be getting that this new prime progression corresponding to new prime is equal to 0, 1, 2, 3 and so on. Corresponding to 0 you have all the label here, and corresponding 1 then you have all the label of this ground state of the levels. In an absorption experiment, on the other hand, this sample is at a room temperature. At such temperature, according to the Boltzmann distribution, and most of the molecules are in a ground state, means only most of the molecules are the new double prime is equal to 0, and very few few atom molecules are excited in the new double prime is equal to 1 or the higher levels. So hence, once we are passing a continuous light source, causes the absorption transmission mostly from the new double prime to the all levels of the vibration level of the excited electronic state. It means that the new prime progression will be getting that. So this is the figure that now it's this. Because the most of the molecules are in a ground state corresponding to new double prime is equal to 0, and a few only molecules are exciting on this new double prime is equal to 1 or the higher level. Then all the progression we are showing here in an absorption spectra from new double prime to the all the higher level of the excited electronic state. So the ground state progression corresponding to new double prime appears to all is very small. Means if I will check this new progression corresponding to ground level, this new prime is equal to 1, 2, 3 and so on. These will be very weak. It's very difficult to observe. And the spectrum, if you look, you check as you are going for the higher energy levels, the transitions taking place for the higher energy level, the difference is reducing. We'll see that mathematically how it is happening, and ultimately you are getting that the continuous one, because this is above this excitation, that is the infinite level, that is above the dissociation of that molecule. So this corresponding to this nu prime is equal to 0 to the transition is taking place, nu prime is equal to infinity, and where this is continuum joints of the bands. So it is joins the continuum band of the molecule. So its analysis, the absorption spectra analysis, gives the useful information about the vibrational level of excited electron state of the molecule. So the importance of the absorption band spectra, we'll see that what are the importances of this spectra. I'm erasing it because I have to write mathematical equations. So the wave numbers of the band origins of a system are given by, now because we are looking for the only this nu prime is equal to 0 to all the above level, then this nu of 0 is equal to nu of E plus of z nu g prime of nu prime minus of z double prime of nu double prime. And you have this nu of E plus z double, this one is omega E prime nu prime plus of half minus omega E x E prime and nu prime plus of half, it's a square, minus this is minus you have this this omega E double prime and nu double prime plus of half minus omega E double prime and x E double prime and nu double prime plus of half, it's a square. So now what we are looking at, the progression from this nu double prime is equal to 0 to the all the above level. It means that we need to put this nu double prime is equal to 0. Finally, then you have this nu E plus of omega E prime of nu prime of half minus omega E prime x E prime of nu prime plus of half, its square, minus here this is nu double prime because it is 0 and this is 0 again. Then you have this plus minus of 1 upon 4 of omega E double prime x E double prime. And once you are taking this as minus sign, this will be positive. Now this is an expression for these transitions, the progressions we have now this expression. So now we have to check the first few bands that are corresponding to nu prime is equal to 0, 1, 2, 3 and so on. So these wave numbers, this is the wave number for the electronic transitions. Then I have to write fewer energy levels corresponding to nu is equal to nu prime is equal to nu double prime is equal to 0, 2 and this nu prime is equal to 0, 1, 2, 3 and so on. These are the wave numbers, this side is the wave number, and we'll see that what is the first difference. So now here this nu of E, this is a common term, this is nu prime is equal to, now you check your expression, then the nu prime is equal to 0, then this is 1 upon 2 omega E prime minus 1 upon 4 omega E prime and x E prime minus 1 upon 2 omega E double prime plus 1 upon 4 x E double prime and omega E double prime. For the next one, this nu E plus of nu prime is 1, 1 plus 1 upon 2, 3 by 2. Then you have 3 by 2 of omega prime minus this is 3 plus this is 3 by 2, it's a square, then 9 upon 4 omega E prime x E prime, and this term remains a constant because you have all these levels from the x double prime, nu prime double prime is equal to 0, x E double prime omega E double prime, and for the higher level then again nu E plus, now it is 2, this is plus 5 by 2 omega E prime minus 25 divided by 4 and omega E prime x E prime minus 1 upon 2 omega E double prime plus 1 upon 4 and this x E double prime and omega E double prime. And similarly for the 3, then you have this nu E plus of 7 by 2 of omega E prime minus 49 divided by 4 omega E prime x E prime minus 1 upon 2 omega E double prime minus 1 upon plus 1 upon 4 x E omega E double prime. Now if you look at the first difference between this and between this, so once you are subtracting them, what you will get that Simply you are getting that this minus this is omega E prime minus of 2xe prime and omega E prime. The difference between these, once you will evaluate, then you will be getting omega E minus 4 of xe prime xe prime. Difference between this one, omega E prime minus 6 of xe prime and omega E prime. This is omega. Now the difference between these labels is omega prime minus 2 xe omega E prime. Difference between these labels, as we are going for the higher levels, you see that the first difference is reducing. That is why these bands, these lines are converging ultimately towards the higher wave number side, and eventually it is a continuous band once it is above this infinite table, that is the dissociation energy excitation. So it shows that this mathematically you can check down now. This nu prime is increasing. The wave number spectrum first difference between the successive bands decreases. The first difference is decreases because this omega E minus 2xe, this is 4, this is 6, then you will get a 8xe. So now once you have this nu prime values is increasing, the first difference is decreasing. This means that it means that the excited electronic state, the vibrational levels, draw closer and closer. They are coming closer and closer. Then finally they are merging. Then you are getting the continuous one. The second difference between the adjacent band is the same. So if you look at it, it is the same. Now the second difference between this one, we have this 2 of xe and omega E prime. Now in the same thing, what we got is the second difference in the emission spectra. We have got the second difference is delta of 2 of z is equal to 2xe omega E. So this is a constant quantity because it's the enharmonicity of this molecule for the excited state. So once this omega prime and xe prime is once this xe prime and omega E prime is measured, that is the known vibrational constant. Known vibrational constant is obtained from the first difference. So the absorption continuum, which joins the discrete bands, this joins the discrete bands. The absorption continuum, which joins the discrete bands at a converge limit corresponding to the dissociation molecule. So where this exactly it joins the two discrete bands with this continuum, and this defines the dissociation energy of the molecule, because after that energy it will dissociate the molecule. So you have this is why it is a very important that in an absorption spectra it is so important, it is providing the dissociation energy of the molecule as well. So the study of the absorption spectra gives more information as compared to my emission spectra, with less my computational approach or the estimation regarding the excited electronic state of the molecule. So now we'll study that. This is all about this electronic band spectra in a absorption. Now we'll do that the absorption spectra of I2 molecule. For I2 molecule, let's estimate what is exactly appearing there. Absorption spectra of I2 molecule, hydrogen molecule. So the energy diagram I'm plotting that you have 0 level or 1. You have this ground state. This is the ground state electronic state. Ground electronic state, and you have excited electronic state. This 0, 1, 2, 3, 4, 5, and so on. This nu prime is equal to 0, nu prime is equal to 1, 2, 3, 4, 5, 6, and so on. So, and above this, suppose I have this nu is equal to infinite. And what I will get, obviously I will be getting that in these transitions, where you have both the transitions from 0 to this, and you have as well this dotted line showing that from the first excited state of this molecule, and this is providing you the completely the continuous spectra. So these are the nu double prime, and these are the my nu prime. So the transition is taking place from here. I'm drawing it with a solid line. From the first excited state, you have this. Then again, you have this transition, then you have this transition. I will explain why I'm plotting these lines. Sorry. So these are the solid lines, are the progression from this nu double prime is equal to 0. These dotted lines are showing the progression from the my nu is equal to 1. So if I will check these transitions, so I will be getting that so you look at this is my nu as the my vibration levels of the excited state, vibrations level of the excited state are increasing, then you have the difference is reducing now. So an electronic band spectra of a molecule when studied under the high resolution is found that to be composed of a large number of lines arranged in a. So now in the case of the absorption spectra of this I2, this iodine gas, so corresponding to the absorption spectra of an I2 molecule, however, shows a progression corresponding to nu single double prime is equal to 0 and even higher in addition to my progression from the 0. So this iodine molecule shows that the progression from 0, nu double prime to 0 and a nu double prime equal to 1 even for the higher energy level, vibration levels as well. The reason is that I2 is a very heavy molecule, so that it has very small vibrational quanta in the ground state. That is, the vibration levels are much closer. So these vibration levels are much closer due to its being a heavy molecule. Even at a room temperature, sufficiently well populated levels at the nu prime double prime is equal to 1 and the higher levels. So at even room temperature. So the absorption transitions taking place from the nu double prime is equal to 0, 1, 2, 3 and so on. But of course, this from the 0, I will have a very intense spectra from the nu double prime is equal to 0 and the nu double prime is equal to 1, and it is decreasing as we are going for the another progression levels corresponding to nu double prime is equal to 2, 3 and so on. So we have this additional progression in the absorption spectra. The progression nu double prime is equal to 1 is indicated by these dotted lines, and this progression from this nu double prime is equal to 0 are represented with the help of the solid lines. So these bands corresponding to nu double prime is equal to 1 can be obtained in a room temperature. So the molecule with a large vibrational quanta, if thick absorbing layers or high pressure are used. So in this case, to achieve this kind of spectra, we use at a large vibrational quanta if the thick absorbing layer or the high pressure are used. So once that we have that container, that the vapor container, we have if I produce a very high pressure, or the thick absorbing. So you have a sufficiently thick layer of this absorbing material, that is gas, then we can find these lines or these spectra of in a absorption case. Now this is the how this electronic band spectra in a absorption is important, because it is a very simple mathematical computation and an observation analysis. You can find out the diffusion energy of the molecule in addition, because because this diffusion energy providing that the separation between these discrete energy levels in a continuous, where it is a continuous one, then you can find out this diffusion energy of the molecule. As we have from the mathematically, we have seen that we are going for the higher level of this the difference is reducing, and slowly this in these gaps, energy gaps are, this first difference is reducing, and ultimately they are merging at the higher and higher wave number side, because this is increasing this side. This is all about the vibrational absorption spectra of a molecule. Now, tomorrow I will be discussing that this rotational structure of the electronic band. So this is the vibrational band, because in this case we have ignored these rotational structures of the electronic band spectra, and tomorrow we'll be considering that the rotational structure of electronic bands. Thank you.